optical physics. So another application to physics occurs in optics. The figure below depicts a wave from the point source S meeting a spherical interface of radius r. So this optics, yes, is a wave of light. Yeah, centered at C, so the radius is centered. So here is a material right here. So here's the source of the light. So it's a wave across like this, propagates straight over here, but in a spherical wave. And then this is another medium, another object, and this has a spherical interface like a lens, like that, where it's centered about this. So the radius is centered about this point over there, C. And the ray SA, so you have SA like this, is refracted or passes through the spherical interface towards P. So when you, so you have a medium over here, for example, air, and this is glass, for example. You're going to have something that looks like this. It's going to go here, hits here, and then it refracts or goes through the medium, and it's going through to the point P. Like that. Yeah, so when this part of the wave hits here, it goes to P. So using Fermat's principle that light travels so as to minimize the time taken, the author of the image, Eugene Hecht, derives the equation. So here's courtesy of Eugene Hecht. Again, it's from my calculus book. So image it over there. And derives this equation, which is n divided by L naught plus n2 divided by Li equals to 1 over r times by n2 times Si divided by Li minus n1 times So or S naught divided by L naught. Like that, or O, or L0, however you want to state it. And again, I'm not going to derive this one in this video, maybe in a future one. But so where N1 and N2 are indexes of refraction, or indices for plural. Indices of refraction, and L naught, L naught, Li, So, and Si are the distances indicated in the figure. So we have this distance, Si, is from P to this external point right there at the spherical interface. So is from the source to this point V. And then you have the Li is from the P to the point A. Then you have Lo from the S to the A, like that. And I'm writing this as capital L just because it's I've never written L like this, and it's just seems a bit different. It seems a bit too ambiguous when I try to put L in. I can't put it in lowercase because it looks like a 1. So I just put it capital L like that. So anyways, and yeah, those are the distances. And also going further, so note that the index of refraction is the ratio of the speed of light in a vacuum over the speed of light in the medium. So that is n equals to C over V. Alright, yeah, now going further, so by the law of cosines referenced from my earlier video below, we can determine the lengths L naught and Li from triangles, or from the triangles ACS and ACP. So you have ACS, and then you have ACP to get the Li. So you have one triangle right here, you have one triangle over here, like that. And we could use the law of cosines because we have an angle over there. So yeah, that's theta r. This one's theta I. This is theta t, like that. Yeah, but the only one we're interested in actually is this one, phi. So that's the one we're interested in, phi, right here between S, A, and C. So we could use, yeah, we can get this one over there. So that's the one we can use. If we know that, then we can solve for the lengths. And again, here's the recall from earlier video on law of cosines. Let's just do this one quickly. And this is going to be, so if you have the points A, capital B, capital C, then the corresponding lengths across here. Yeah, so if these are the angles as well, so this is angle A, this is angle B, angle C, like that, just leave it like that, so pretty obvious. And then the corresponding lengths is B, this is A, and this is C on the opposite side, given by these formulas. So A squared equals B squared plus C squared minus 2BC cos A. So if it's the A one, like if you're dealing with this angle, you can get this one, A squared equals 2, and then B squared, then the opposite ones add up, subtracted by BC. And then if you want to get the C1, the exact same, but now it's going to be C squared, and this one's going to be minus 2AB. So the opposite sides. Anyway, so thus we can follow. Thus we can derive the following equation 3, and that's what we'll call it, which is actually a pair of equations for both of the lengths. So let's look at this one here. So let's look at ACS, or in other words, this triangle with the LO, and there's a phi right there, that angle phi. So let's draw this one out like that. So it's going to look something like this. So there's the interface, or better yet, let's draw this in red. So there's the interface like that. And now let's draw this in black. And now we're going to have the points like this. So this is points across here. Yeah, let's draw the first point. It's going to be at C. See how far away this is to make it look like that. Alright, so this is going to be C. Let's just draw it over here. I'll just move it over here. So this is going to be C. This is going to be our point P. But before we get to that, just to make it less stuff in the way, this is going to be our S. This is going to be our A. Goes like that. This is our point A. And there is our spherical interface. This has a radius R. This is radius R, centered about the point C like that. And again, let's just look at this one. Yeah, so we have it here, centered about there. So this is distance R from here to here. And yeah, that's a sphere across there. And we have the point LO, and this is the phi angle. So this is going to be, I'm just going to write this as phi. I'll just put this for completeness. This is going to be our phi angle. This is our L0, like that. And now this distance across from here to here is our SO. Yeah, that's our SO. So that is, yeah, this is SO. The next one's going to be, this is R across to this point. So that means, well, we can, we know the full length of this one's going to be SO plus R. So we could use this equation, the law of cosines. So now we're going to pick our point is going to be, remember, this is going to be squared, and then we'll have the, we'll have the other sides squared and add up, and then minus 2 times those sides. So in this case, this is going to be our angle. So this is going to be our, here, and also what we're going to do is take the, let's do this all in one go. Take the square root and take the positive side of the square root. Because, yeah, so we'll have a square root, because it's squared like that. So that's the length of the opposite side. So opposite side is LO, and then we're going to have the other side squared. So this is going to be R, that's one side, and the other side is these two together. So we're going to have R squared plus SO plus R squared minus 2 times those sides. It's going to be 2 times R times SO plus R. And then we're going to have cosine, because again, it's the law of cosines, phi. It's cosine this angle. Phi, like that. And now this is, yeah, this is our equation 3, but part A of equation 3. And then the next one's going to be, well, Li. So now we got to solve for Li, which is in the equation. And let's look at how it looks like. Yeah, so there's our Li's from APC. So from this triangle over there. So now we're going to have to get the point P and then start solving for this Li. So let's go over here. So this is going to be across like that. Let's just draw this a bit better. I'm going to move this R underneath, so it's not in the way. Then this point here is going to be our point P, like that. Now this angle, this one right here is the one we want, because this is our Li, so we need this angle. Now this angle right there is going to be, well, we know this one is going to be just pi. This is 180 degrees minus that phi. This is just going to be pi minus phi. Like that. I'm just going to draw this better. Alright, here, just fix that up to make room in there. Now this distance across here, well, this one's going to be, well, we know this distance across from this point all the way across to P is our SI. That's from this one right here. Yeah, so that's from this endpoint from V to all the way to P is SI. So that means this one's going to be just SI minus R. Yeah, so that's what we get is from here to here is SI minus R, which is this point across there. So that's what we have is, now this is going to be slightly different than our other one. So one of the sides is going to be R. So Li square root is going to be the positive square root. It's going to be Li, and then plus R. One of the sides, so we're using the law of cosines, R plus the other side squared. SI minus R squared, and then minus 2 times R times SI minus R, and now we're going to do cosine of this one, pi minus phi. Cosine pi minus phi. Yeah, so this one here looks a bit different than this one, and that's because of the pi minus phi, so we have to use another trig identity. So again, let's just scroll to that. No, actually, no, I'm not scrolling. I don't know why I'm scrolling. But anyways, so now the next step is, well, this is going to equal to this pi minus phi is equal to just negative cosine pi, so we can simplify this as r squared plus si, and I'll show the derivation in a bit soon, or just the identity proof. This is going to be plus 2r si, make the si as a subscript. Okay, so this is going to be minus r cosine phi, like that. And this is, put this better, square root, like that. And we'll just put a quick recall for the cosine rule. So recall, if you have like this, let's say you have a xy axis like that, and now you have a triangle like this. This is our phi, so this angle's phi, and then we have the sides b, let's say this is a, b, c, and hypotenuse c, so cosine phi equals to a over adjacent over hypotenuse, so a over c. And then now if we look at the pi minus phi, it's gonna, if we scroll all the way across here, this angle, it gets all the way here. Actually, before I do that, let's just draw a mirror of it like this. So this is gonna be our mirror, this is b, this is gonna be our phi, like that, going from the other side. Now this is gonna be our c, and this is our negative a. So then this angle from here to here is going to be our pi minus phi. So in other words, the cosine of pi minus phi is just equal to, again, adjacent over hypotenuse is going to be, because remember that's all that the trig is. It's just a ratio of that the angles make. So when you get past this 90 degrees, you get this pi minus phi is going to equal to negative a over c. Equals negative a over c, which equals to, this just equals to cosine phi. Negative cosine phi. Negative cosine phi. And we throw that inside the above. Alright, so I just want to close that up. So that is what we have, and now these are our equation 3. We'll call it equation 3. We get this one and this one here. And we'll be using it throughout this video, which has a lot more exercises to come. Alright, so thus we can carry on. So the above equation 3, so that's this is equation 3, these two, makes the earlier equation 1 cumbersome to work with, and that equation 1 is over here, this formula. So now you're going to divide by Li, where Li is going to be this giant square root formula with a cosine. So it's cumbersome to work with, or hard to work with, which is why Carl Friedrich Gauss in 1841 simplified it by using the linear approximation cosine phi is approximately equal to 1 for small values of phi. Note that this amounts to using the Taylor polynomial of degree 1, since the odd power is equal to 0. And what I mean by that is, let's just write the Taylor polynomial for this. Cosine of x is equal to, and let's just scroll all the way up for this. And here's the, just scroll up to table 1 from earlier videos. So cosine of x is equal to 1 minus x squared divided by 2 factorial plus x4, and then minus, etc. So it goes powers of even powers there, and the radius of convergence is infinity. So let's scroll back. So teleport it back here. So cosine of x is equal to 1 plus, and now, so it just has the even powers, but that means the odd powers are equal to 0. So it's actually written like this. So this is 1 plus 0. This is going to be our 0th degree. This is our first degree, and then it goes to minus x squared over 2 factorial. And then it goes to plus 0, and then we're going to get another plus x4, because all the powers of the odd ones are cancelled out. So 4 factorial, then minus, the next one's going to be, you have the fifth one's going to be 0, so it just goes minus x, the 6 factorial, plus dot dot dot, plus minus dot dot dot. Let's write it like that, because it's alternating. And we have r, radius of convergence is infinity, like that. So that means that this is going to be degree 1 is over from here to here. This is degree 1. T1 of x, in this case, is equal to T0 of x. So it's degree 1, even though, it's the same as degree 0. So T1 equals T0, and likewise, if we want to go all the way across to here, this is going to be our second, this is going to be our third degree. So T3 of x is equal to T2 of x, because we have a 0 there. Like that. Yeah, so now with this approximation that cosine phi is equal to 1, then equation 1 becomes, and this, remember equation 1's over here, this right here, this becomes the following simpler equation, which we are asked to show in exercise 2a later in this video, and that's actually going to be called equation 3. This is actually, change this all to equation 2, I got these a bit mixed up. This is equation 2. Like that. So yeah, this is equation 2. The next one's going to be equation 3. So I'll solve this in exercise 2a. Basically what happens is when you plug in this estimation, we're going to get n1, so much simpler than before, s0 plus n2 over si equals to n2 minus n1 over r. So yeah, so that's what we get, and this is much simpler than, so there's the equation 1 over here. So we get the same left side, just actually no, not the same left side because it has the different si. So we're gonna get n1 over so instead of this lo, and see this. So we get rid of all of these li's and we just get it with a simpler function. So it's much simpler to deal with, and you don't need to work with these giant formulas over there. And yeah, basically the equation 3 just removes those distances. Yeah, and the only distances we have now is SO and SI, which are just the basic flat horizontal lines right here. SO to the point, and all of a sudden to the point P where it refracts 2. It's just fascinating stuff. So now let's keep going further. So yes, that was equation 3. So the resulting optical theory is known as Gaussian optics, or first order optics, is using the first order approximation, and has become the basic theoretical tool used to design lenses. A more accurate theory is obtained by approximating cosine phi by its Taylor polynomial of degree 3, which is the same as a Taylor polynomial of degree 2. Again, I've written that over here. So degree 3 is the same as degree 2. So we're just going to use now 1 plus or 1 minus x squared over 2 factorial. Yeah, so this takes into account rays for which phi is not so small, that is, rays that strike the surface at a greater distance h above the axis. So yeah, so when you have a higher order approximation, you can take into account further distance across here. So bigger angles phi like that. So where the rays strike higher up on this surface over there, and you can more accurately measure or model or calculate. So anyways, let's go to equation 4. So what happens if we put the second order, and we're going to have to do this in exercise 2b, what we'll get is, we'll get n1 over s0 plus n2 over si equals 2, and then this is going to be n2 minus n1 over r, which is similar to our starting point right here. And then all of a sudden we're going to have to add a term, so we're going to have h squared. So now we have distance here for that height, and then this is going to be n1. Whoops. I just fixed that up. I don't know, my computer OneNote glitches sometimes. Anyway, so this is going to be h squared times by n1 over 2s0 or so, and then times it by, this is going to be 1 over s0 plus 1 over r, and that's all squares. So it's much more complicated than before, and it keeps going on. So one more term like this is going to be plus n2 over 2si, and then 1 over r minus 1 over si, like that. And this is squared, and block that out like that. Yes, and this giant formula is known, or the resulting optical theory is known as third order optics. Let's make this a bit neater like that.